Okay, so today we're going to start talking about the standard normal distribution. Most of you were in the lessons for these, so this should be a recap, this part. And we're going to start by identifying Z. And it says Z is the number of standard deviations above the mean. So hopefully you remember the parameters and how they fit in our normal distribution. So go ahead and pause it and see if you can answer the Z values for these. Okay, so since it's the number of standard deviations above the mean, 100 is my mean, so it is no standard deviations above itself. 130 is 30 from the mean, and that is 2 standard deviations. 85 is below the mean. In fact, it's 15 below. So since Z is always the number of standard deviations above the mean, it'll be negative in this case, because it's -1 standard deviations above the mean, or it's 1 standard deviation below. So again, go ahead and pause it and try and finish it if you didn't know where to go. See if you can use that to help you. All right, you should have gotten 4 1/3 or 4.3 recurring. And for the last one, you should have gotten negative 2.5. Okay, so I want you to take a minute right now and think about what is the process. How do we code from our value that's in our distribution to our Z value? Go ahead and see if you can figure it out and pause the video while you write it down. Now, hopefully you started with that Z would be X minus mu, as that's what you see we've done here as we were doing our first few. But we didn't stop at 30. We then got to 2 by dividing by our standard deviation. And that is how we code a value in Z. And remember, Z is the number of standard deviations above the mean. Why don't you go ahead and see if you can finish the rest of this video. All right, go ahead and check your answers. Do you remember something that may have caught you out if you're seeing that you got different answers? Is that standard deviation is always written as sigma squared. And they don't have to give it to you that way. They can have actually squared sigma. So in this case, sigma is 2, not 4. So if you got different values there, check and see if you used your sigma as 4 instead of 2. So this is known as the standard normal distribution. And the standard normal distribution, if you refer to our tables that we had just done, every single time, once we changed it to a Z distribution, it was distributed normally still, but the mean always became 0, because it was 0 standard deviations above itself. And 1 standard deviation away always was 1. So this is something that you do need to know, and that is that Z is always coded by taking the value you have and subtracting it from mu and dividing by sigma to turn it into a Z value. And Z values always work as a normal distribution of mean of 0 and standard deviation of 1. So then everything we did in our past few lessons will still be able to work now. We just would know if they ever use the value of Z to use the mean of 0 and the standard deviation of 1. Okay, so we're going to try using this sum. So don't forget again that Z means we need to put it into this situation and our coding. So we're going to, like I said, see if we can do the work that we were doing in the previous 2 sections, but in terms of Z. This first one is the probability it wants us to find of Z being greater than -1.3. Now, because I want to find the probability, I know I'm going to be using, let me just see if I can get that a little bit clearer for you. One moment. All right, hopefully you can see that a little better now. So what we're going to do, let me refocus it. Yeah, there we go. For this first one, because we're trying to find the probability, I always start by doing my sketch, and it's negative. So a benefit of being a normal distribution is because the mean of any normal distribution is here, with being in Z, I know a negative one is going to be to the left of the mean. So that would be where my negative 1.3 is. And I want to find the probability that I am above this mean. So I want to find that area. So I know that I need to go to my calculator and menu 7 to get my distribution. And as I'm finding the probability, I'm going to use number 2, which is our normal cumulative. Our lower boundary for our range that we're trying to find is here, the one we just had, negative 1.3. And our upper bound, remember, we assume all probability lies within 5 standard deviations. So as long as you say 5 or higher, you're good. But I always do 10,000 because it's unlikely that any normal distribution is above that. As you notice, normally we put in our standard deviation, which is 1, and hey, the calculator already says that. And we do our mean, which is 0. So your calculator's default is in fact to use the Z distribution, but it's still always good practice to check to make sure those numbers are there. And we get the probability of being approximately 0.9031995,154. Now again, remember I always say more digits is better than not. And so I'm going to give this as 0.90320. Now if I kept all the digits, I'd be fine. If they don't specify, do feel free to make it as accurate as you want, but be careful not to round too soon. So go ahead again, if that helped you, and see if you can do number 2 as it follows a similar pattern. Okay, so I've drawn my sketch already. One thing I've made sure of is that they aren't symmetrical about the mean. The mean is 0, so 1 should be closer to it than negative 2. So I have both my bounds, standard deviation and mean, and there's our value. Okay, so C is a bit different. This time we're given the probability. We know that larger than A is 0.7%. So when I do my sketch, halfway will be 50%. So I'm going to go a little bit more. And there's some value A. And this space in here is 0.7. Now from the work we did previously, we do know that in order to use our calculator to help us find the missing value, we need the percentage before it. So I'm going to use the fact that the probability that Z is less than A is 0.3. And I got that because all probability adds up to 1. This time when I go to menu, I'm going to hit 7, but we're going to use the inverse. So our area, as we know, area represents the probability, so it'll be 0.3. And again, it automatically uses the default as the standard deviation and mean of a Z distribution, but good practice to always check. And so then that's our A value there, negative 0.52440. Right, and again, it does make sense. We're definitely less than the mean. The mean is 0, and our answer ended up being a negative value. Normal distribution helps us with being able to see if our answer makes sense. Okay, so as you can see as I did this next sketch, I changed where A was slightly, so it's on the later end, and that's because it's symmetrical. If they're just opposites of each other, and the mean is 0, they'd be perfectly symmetrical around the mean. If the shaded space is 0.6, that means the unshaded space is 0.4, which means the part before the negative A isn't 0.4, but 0.2. So again, by using my inverse function, 0.2 in standard deviation of the normal, and we get our A value. Well, actually this is our minus A value. So we can say that negative A is negative 0.84162. So positive A is 84.162%. Obviously, either way is fine unless it specifies. So as you can see so far, once we're in Z, it works exactly the same as any normal distribution. You just need to remember that the mean is 0 and the standard deviation is 1. Because all the problems have to give you is that they are in Z. The Z variable is only used in reference to this distribution if they talk about it as a distribution. So if you're asked for it, again, you need to know this. As Z is used often, and normally when we talk about probability, we're talking about the probability before a given value. We have a shortcut, which is phi Z. So if you see something that says phi Z, it is another way of saying the probability that your Z value is less than whatever value you were just given. So if I want to show the probability that Z is more than a given value, I would say that's the same as saying 1 minus the probability that it is less than that given value. And once I have it in terms of the probability of less than, I can use phi. So phi 1 minus phi of Z. Got ahead of myself there. So 1 minus phi of Z. I'm going to rewrite that there for you so it's a little clearer. 1 minus phi of Z. So let's try some problems like that. If I ask you for the probability that x is less than 53 in terms, so I don't know what's with my writing today, terms of phi Z. So it wants me to write this in terms of phi. Now phi always means that I am in a Z value, which remember is the number of standard deviations we are above a mean. So if we're given this and it's an x, we must have some other information. So we need to be given the distribution of x. So in this case we're going to have that be 50 with a standard deviation of 4. And now we can do some coding. So we can say that Z equals 53 minus our mean divided by our standard deviation. So it is 3/4. And the moment we have it in that, we can say that we're looking for the probability that Z is less than 3/4, which is correct, but they want it in terms of phi. So we will say that we are looking for phi 3/4. Okay, so in this problem, same distribution for x, but we're looking for the probability that x is greater than or equal to 55. So we want to write in terms of phi Z. So we first need to code it. So we will take our value, subtract the mean, and divide by our standard deviation, which will give us 1 and 1/4, or 2/5. right? So that's great. We now know that we are looking for the probability that z is greater than or equal to 1.25. However, they want us to do this in terms of phi z. And to do this in terms of phi z, we need to first change it to a less than. So it'll be 1 minus the probability that z is less than 1.25, which means it's 1 minus phi 1.25. And that's using phi to represent probability in terms of z. With all that information, you should be able to try exercise D now, and then come back later to see how we can use standardization to help us with what if we don't know the mean and standard deviation of our normal distribution.